Hello everyone. Last time I have covered the setup for the Nand2Tetris software and the setup file for workshops and assignments. This time I will continue to cover workshop 1 activities. Last time we have stopped here the usage of hardware simulator with test file input. Let's open up PowerShell. The hardware simulator can be also used in GUI, graphic user interface, with no input parameters following the batch file. The GUI window will pop off shortly. Okay, here it is. You can press this button to load the chip. Go to the course where I stored 2022 S1 CS Workshop 01 the and HDL file. It will appear here, the implementations. For now it is empty. And I can also load a test file here and .test. Using this graphic user interface, I can step over those test script. At the end of this execution, output result file will be generated. It is here. This is the truth table of the execution. Let's complete the implementation of AND gate and then come back later. You can check your result by running make command. Let's do it here. Go to Linux. Okay, run make command. Cannot remove and.out permission denied. Okay, you can see all of those tests failed because I have did nothing. chmod 777 to .out and run make again. Still denied. because this Nand.out is created by GUI program, so the make marking program cannot delete it. Let's delete it manually. Okay, because this is still running, so close it, then retry. CLER clear. To make again. Perfect. In this Nand2Tetris project, initially we only have a Nand gate, so we need to implement all those stuff starting from the Nand gate. So what is a Nand gate? Let's use this one. Here at the top is a symbol of the Nand gate. You can see it is basically an AND gate and a NOT gate combined together, Nand. And this Boolean equation to express a Nand operation. And here's a truth table. A Nand gate has two inputs, input A and input B, output Q. You can see the Q is defined by A and B. We can use this Nand gate to build a NOT gate. Different from the Nand gate, the NOT gate only has one input, let's call it in, and one output. Out equals not in. The truth table will be like this. Zero, one, and the output is inverted of input, so it's 1, 0. So what can we do to build a NOT gate from Nand gate? Let's focus on those two lines. If both the input are the same, you can say the output of a Nand gate is just the inverse of either the input. So we can build our NOT gate from Nand gate by connecting, by shorting the input of the Nand gate. Like this. Shorten it and feed from the same point. Okay, this connection converts the Nand gate into a NOT gate. Let's code it in our Nand2Tetris program. Where's the HDL file? not.hdl. Not .hdl here. Code date. For starter, we only have a NAND gate. NAND, it has two inputs. A. Let's connect A to the input pin, which is defined as N. Like as we talked about, we should short the two inputs and feed with the same signal. So we do this. B equals N. So both A and B pins feed with the same signal, in signal, and the out signal is connected to the out of the out layer NOT gate. Don't forget the semicolon. So then our NOT gate is done. Let's try to run our makefile and see what's the result. As you can see, our NOT gate passed the test, so our implementation is correct. Next, we will to see how to build AND gate from the NAND and NOT gate we just implemented. Okay, let's see. Make an AND gate. We already have those two gates, the NAND and NOT. So basically, the AND is the combination of an AND which we want and a NOT gate. If there's another NOT gate, the two logic inverse will be cancelled. So let's try this, cascading one NAND gate and a NOT gate. Where's the AND? Okay, we have a NAND gate with input A. The input A of NAND gate is connected to the input signal of AND gate. So A equals A, comma, B equals B, comma, and we can make another intermediate signal. Let's call it C. Out equals C. Okay, that's our NAND gate. We have just implemented NOT gate. Let's put the in signal as C and out signal to the out of the AND gate. Semicolon, and save and close to see what happens. Linux make. Okay, that's great. So we have both NOT and AND gate correctly implemented. So next exercise would be a NOT gate. Let's delete. Okay, let's do this. How to select? Doesn't matter. Select all, delete. How can we build an OR gate from NAND and NOT? Let's see what is a NOT gate. No, sorry. OR gate. Here's a sample and the truth table of OR gate. So how can we build it from the NAND and OR gate we have? From this to that. The truth table is like this. NAND and O. Q equals and A times B, a bar. There's a distribution rate, so Q also equals A bar, but this time it's all B bar. Cancel this NOT. NOT gate feed into the Let's go back to the lecture. Boolean arithmetic. Exclusive all. Difference and yeah, here it is. Nand. This is distributed to all equals Nand. Yeah. Yeah. Let's use this law. X or y equals not x and not y, then not. A or B equals not A and not B, not. So that basically have two parts, two hierarchies. That's first level and then the second level. So it is like this, a NOT gate of A into a NOT gate, B also into a NOT gate. The output is faded into a OR, AND gate, and there's a NOT at the end. This is equivalent to a OR gate. Let's implement it in hardware description language, HDL. So where's all? Okay, it is here. With what we just said, not A, then not B, and fit into a NAND. The input of a NOT gate is connected to A, and the output is an intermediate value. Let's call it NOT NA. Not A means not A. Another NOT gate input connected to B, and the output let's make it not B, NB, followed by a NAND gate. A equals NA, B equals NB. The output is our out signal of the OR gate. So slow. Okay, go to make. Pass, yeah. Let's continue to work on XOR, exclusive OR gate. So here is a symbol and a truth table of exclusive OR gate. Let's delete some more and start from here. Exclusive OR gate. The equation symbol and the truth table of exclusive OR is showing here. As you can see, when the two inputs are different, in that case the exclusive OR will be 1. Otherwise, if those two inputs are the same, XOR will give a 0. So how can we build this exclusive OR from 3 gates we already have, NAND, NOT, and AND. Also we got OR. So let's write down the truth table of the gates we have. Let's continue to write it here. NAND and OR. For NAND, it is like this: 1 1 1 0, and the AND is inverse of NAND, 0 0 0 1. And for the OR, that's 0 1 1 1. So let's see how can we combine those three to make a exclusive OR. NAND. Yeah. If we combine the NAND and the OR and feed it into a AND, it will pick up the overlapping part. 1 and 0 is 0, 1 and 1 is 1, 1 and 1 is 1, 0 and 1 is 0, so it's exactly what we want. So let's do this. NAND gate. An OR gate. Sharp enough. Feed into a AND gate. So that's our input A, and that's our input B, the output. Let's go back to HDL and have a try. Find the XOR exclusive OR here. What we want is in the first level, NAND OR. NAND A equals A, B equals B. Put an intermediate value, output it as NA. What we have? OR gate. equals A, B equals B, odd equals OA, odd gate A. The second layer, that's AND gate. So AND gate A equals NA, B equals OA, odd equals odd. Okay, save and have a try. This is my Windows. Okay, here. Clear first. Make. Waiting for result. Exclusive. Oh, it seems failed. So let's have a look what's wrong. The output file of exclusive all. Okay. Why it only have two lines? 0, 1, 0. So it failed here. 0, 1. When A is 0, B is 1, the output should be 1. Let's use a GUI to debug. Okay. Load up our RAM here. C drive. For the 2020 semester 1 computer systems workshop 1 XOR exclusive all. It's empty. Where I just had why it's empty? XOR HDL. Did I save this? Don't know. Oh, okay. I'm at the wrong folder. So here is previous years. Let's close this. You can also do file editing. No, you can't. Okay, close it. Can't do it here. C drive. (2022). That's one. Computer systems. Workshop 1 xor.hdl. Okay. Let's do it again. Nand or and. NA. Oh. Odd equals OA. What else? AND gate. This time it should work. 2022 semester 1 CS workshop exclusive. Close the text editor. Okay. Load the exclusive. Okay, the implementation is not here. Then load the test file. Okay, comparison ended successfully. That means the implementation should be correct. Let's use our make file and see. Pass. Yeah. Cool. Next, let's try NOT 16. NOT 16 means 16 NOT gates in a row. This will process a bus. Bus means multiple signals aggregated in parallel. So that will be looks like this. A bus with 16 bits, and this can be split into multiple strands. In total, there are 16. So each of these signal has a NOT gate on it. 16 in total, and also the output is 16. This is pretty simple. Let's do it in HDL. Not 16. Okay, the bus in HDL is represented like this, pretty much similar to the array in programming language. What we need to do is to create 16 NOT gates, English input method. not a equals in 0. No, for not get there's no a, it's called in. Out equals out 0. I will copy and paste also the this statement 16 times. 1, 2, 3, 15 times. So there are 8 in a group. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And I change this to 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. In some high-level HDL, you can do this in for loop to generate hardware instances. However, in Nand2Tetris, I don't know whether I can do this. I will find it out later. For now, just copy and paste. Ah, 15. From 0 to 15, 0 to 15. That's it. Let's save and have a try. Okay, the Node 16 gate is created successfully. The rest, and 16 or 8V should be similar to our Node 16 gate. So that's our content today. One thing you need to notice is that all 8-way isn't 8 all in parallel. It is a huge OR that takes 8 inputs and produce one single output. I will demonstrate this. No. Let's remove this. What 8-way OR looks like is like this, a very large OR gate. Instead of take just 2 inputs, it takes 8 inputs at once. So that's IN 0 ... to IN 7. From 0 to 7, that's 8 bits, and output a single out. To implement this, we would need 3 layers. In the first layer, we will have 4 double input OR gates. And as a second layer, use two double input OR gates to sum up the outputs from the first layer. And as a third layer, one single OR gate and one output bit. So let's implement this in HDL. O8V. Okay. Layer. First layer. Oh. A equals in 0 and B equals in 1. Out equals O10 and copy this statement 4 times because we got four OR gates as the first layer. Second layer we got two OR gates, and the third layer one single OR gate. Now modify this input number 0, 1, 2, 3, 4, 5, 6, 7, or 1, 0, 1, 1, 1, 2, 1, 3. So this as the second layer is not an input signal anymore. We need those intermediate signals. 010, 011, not 0, 011. Output is 020, 012, 013. Output is 021. The third layer is 020, 021. Output is just the output of the large OR gate. Okay, let's save this and execute to see what happens. Clear, make. Okay, our O8V gate passed the test. Let's skip over those demarks and do marks first. So what is a mask gate? In lecture we have this one. This triangle is a mask gate. It has 2 inputs and 1 selection input. So if selection is 0, see those lines with selection with 0, the output is exactly the same as input A, and regardless of what value is presented in input B. So if selection input is 1, the output depends on the input B, not related to input A anymore. So let's design our marks. When selection gate is 0, the output is always depends on input A, so it should be an AND gate somehow. This input is when it is 0, select this one, so it has a NOT gate here, SEL, selection input and input A. This is there. When selection is 1, so let's skip this or NOT gate. See what happens here. When selection is 1, so this is 1, it will take the value of input B. So let's see how can we sum those two signals together. When selection is 0, should ignore whatever B is. Ignore. How can we ignore? Let's see our lecture notes. If so when SEL is 1, so regardless of A, this signal is always 0. Then the value is depends on 1 depends on B. So I think if this is always 0, and simple OR gate should work. If selection signal is 0, this here is 1, and this signal will be exactly the same as A, and 0 to here, B and 0 always be 0, so some value or 0 should be take the value of some value, so vice versa. Let's try this out. Max. What we have is first we have a NOT gate. Selection put in NOT gate, call it NSEL, not SEL. English input method. Not in equals SEL. Out equals NSEL. The second layer a couple of AND gate. The first AND gate will take A as NSEL. Input A as NSEL, right? B as A. Out as called A10. Another AND gate. A is just SEL. B is B. Out. Let's name it as A11. What is the third layer? A simple OR gate. A is A10. B is A11. Followed by out. Out is the output signal of the marks. Out. Finish and save it. Okay, run a makefile and see the result. Okay, it seems our implementation is correct. So let's continue to work on Dmax. What is Dmax? It seems not covered in lecture. Let me explain what is Dmax. Dmax is just the reverse function of the max. Here is an in signal. Similar to the max, it also has a SEL. And will have two outputs, A and B. When SEL is 0, the in goes to output A, and B is kept 0. When SEL is 1, in signal goes to B, and A is kept 0. So let's see how can we do this. SEL is 0. So similar to this, we will have a NOT gate. When this 0 in is goes to A. 0 go to NOT gate will give 1. 1 and AND gate in goes to A. So whenever SEL is 1, it will becomes 0. 0 and any value will give 0. Kept A 0. So the second input looks like this. SEL, when this is 1, the in is goes to this AND gate, and output B. Okay. Let's try this out in HDL. Dmax. Demultiplexer. That's CMP file. Where's AD? And here, HDL file. I'm running a screen recorder on my laptop. It makes my laptop reaction pretty slow. I don't have a digitizer TV card. Otherwise, I can capture the screen using another computer. Hope I can ask Ian to buy one. Let's see what's that. First layer NOT gate. NOT gate has an input which is in, the in signal of Dmax. Call the output as NSEL. That's the first layer. Second layer will be two identical AND gates. A is NSEL. B is what is in signal. In signal goes here. Output is A signal. Another AND gate. A is SEL. B is in signal. Output is B signal. Yeah, that's it. Save and close. Slow. Why? Slow. Have you ever seen giant panda in Adelaide Zoo? It is said the only giant pandas in the southern hemisphere. I got a booklet talking about this. Giant panda. Why so slow? Okay, anyway, let's go and use this. Clear, make. Dmax test failed. Let's see why. ABSEL in. Oh, I put in this. And here. That doesn't work. How can I switch to my whiteboard. I accidentally put a in signal here, so let's go back. Should be SEL selection signal. This time should work. Clear, make. Okay, it works. It works. Our dim max. So the rest stuff should be straightforward. Just cascading the gates we already implemented. So I let you to try them out on your own.